Hello, my name is Javier Vela and I'm an assistant professor of chemistry at Iowa State University and a faculty scientist at the Ames Laboratory. In this video, we want to highlight how we've used our background in small molecule inorganic chemistry, organometallic chemistry, and catalysis to address some of the outstanding challenges in the field of colloidal semiconductor nanocrystals.
While researching the synthesis of one-dimensional nanostructures for photocatalysis, our group discovered the spontaneous formation of axial composition gradient and phase segregation in ternary semiconductor nanorods. After further study, we found that we could possibly suppress or induce such composition gradient along axial or even radial directions by simply modifying the chemical reactivity of chalcogenide precursors. We believe this is because the transition state energy for the reaction rate determines that nucleation is closest to the energy of molecular precursors than to the energy of much more stable nanocrystals. So, by tuning the sterics and electronics and thus manipulating the chemical reactivity of molecular precursors, it is possible to fine-tune the nucleation rate of different nanocrystalline phases.
Molecular chemists use photochemistry to generate highly reactive species. Light could also be an ideal tool for building metastable nanomaterials because light-induced reactions proceed through alternate pathways at low temperature. We have employed whole flask illumination methods for two different purposes. One is photodeposition of surface-bound metal particles on colloidal semiconductor nanorods with high site selectivity, while the other is the synthesis of very small cobalt oxide nanocrystals. As we explored electronic interactions between soluble transition metal complexes and quantum dots, we found that irradiating aqueous solutions of cobalt coordination complexes produces small cobalt oxyhydroxide nanocrystals with a diameter of about 3 nanometers. In the absence of light, the same reaction doesn't proceed unless the solution is heated to 80 degrees Celsius overnight. The resulting nanocrystal aggregates are about 250 nanometers across. Low-temperature photochemical synthesis could also be applied to the preparation of chemically doped nanocrystals. These are hard to make by conventional high-temperature methods because the doped impurities are only a few lattice parameters away from the nanocrystal surface, and they're easily extruded at typical colloidal synthesis temperatures.
Using the semiconductor metal heterostructures that we made by low-temperature photodeposition, we have explored the photocatalytic conversion of biomass-relevant substrates. In contrast to photocatalytic water splitting, which has been studied for many years, photocatalytic conversion of biomass is a relatively new and potentially transformative concept in renewable energy. For example, dehydrogenation or hydrogenolysis of polyols could produce renewable fuels such as hydrogen or hydrocarbons respectively. We have used semiconductor metal nanostructures for sunlight-driven dehydrogenation and hydrogenolysis of benzyl alcohol as a model. The heterostructure's exact composition determines photocatalytic activity or turnover as well as product distribution. A few metal islands on the semiconductor surface greatly enhance activity and selectivity and prevent photocatalyst itching and degradation. Platinum-modified nanorods favor hydrogen production, whereas palladium-modified nanorods favor toluene.
Quantum dot surface modification is most commonly performed by thiol-ligand exchange. This method consists of replacing the nanocrystal's native ligands with carboxylate or amine-terminated thiols, usually added in excess. Unfortunately, removing the nanocrystal's native ligands can cause etching and introduce surface defects, affecting the nanocrystal's optical properties. In addition, ligand exchange methods are unable to control the extent of surface modification or number of functional groups introduced per nanocrystal. We have reported that surface-doped nanocrystals can be made not only by ligand exchange, as it has been done routinely in the past, but by direct nanocrystal synthesis in the presence of 2 or more different calving ligands. Simply varying the active to inactive ligand ratio used during the nanocrystal synthesis allows controlling the number of chemically active groups or valence per nanocrystal. We have also used infrared and multidimensional NMR to investigate the changes in ligand organization, surface chemistry, and overall nanocrystal properties that arise as a result of surface doping.
We believe this work will positively impact the field of photoactive semiconductor nanocrystals and their application to catalysis, energy conversion, and biology. We also hope that this work will help bridge the gap between molecular chemistry and nanotechnology. We trust that you will find our perspective interesting and look forward to receiving feedback from JPC Letters readers and viewers.